Imagine, if you will, stepping out of a time machine into the air of a long-vanished world. You take a deep, experimental breath. The air feels different, somehow thicker, more substantial. It is invigorating, rushing into your lungs with an almost electric intensity. Your senses feel heightened, your mind sharper, your body humming with an unfamiliar energy. This is not the thin, nitrogen-diluted air of our 21st century Earth, with its life-sustaining but modest 21% oxygen. This is the atmosphere of the late Carboniferous and early Permian periods, roughly 300 million years ago. This is a world where the air itself contained a staggering 35% oxygen. The story of Earth is written in the chemical composition of its atmosphere, a dynamic and ever-changing veil that has been both a cradle and a crucible for life. From its violent, molten beginnings, shrouded in clouds of carbon dioxide and methane, to the nitrogen-oxygen balance we know today, our planet's air has been in a constant state of flux, driven by the relentless forces of geology and biology. Life and its environment are locked in an intricate dance, each shaping the other in a feedback loop that has lasted for billions of years. And in this grand narrative, few chapters are as dramatic, as bizarre, or as profoundly transformative as the era of hyperoxia, the time of too much oxygen. We often think of oxygen as an unalloyed good, the very essence of life, the molecule that powers our cells, the element that makes complex animal life possible. And this is true. The Great Oxidation Event, over 2 billion years ago, was a catastrophic pollution crisis caused by the first cyanobacteria, which forever changed the planet's destiny by filling the skies with this toxic, reactive waste product, oxygen. But like all good things, oxygen has a dark side. In high concentrations, it becomes a destructive force, a potent catalyst of combustion and decay, and a dangerous toxin that can ravage living cells. The difference between medicine and poison, as the old adage goes, is often merely the dose. This narrative is the story of that high dose. It is a journey back to a time when Earth's forests were unlike anything seen before or since, when insects grew to monstrous proportions, and when the very chemistry of fire and decomposition operated under different rules. We will explore how a planet can accidentally brew such an oxygen-rich atmosphere, examining the intricate geological and biological machinery that first produced and then trapped colossal amounts of organic carbon, effectively preventing it from recombining with the oxygen in the air. We will walk through the vast swampy rainforests of the Carboniferous, where towering club masses and tree ferns laid the foundation for this atmospheric anomaly, their fallen remains not rotting away, but piling up in layers that would one day become the coal that powers our modern civilization. We will witness the life that thrived in this supercharged world. Dragonflies with the wingspans of hawks patrolled the skies, and millipedes the length of cars crawled through the thick undergrowth. But this was not a simple age of giants. It was an era of intense evolutionary innovation and pressure, where the high-oxygen environment influenced everything from lung efficiency and circulatory systems to the very structure of eggs and the strategies of predation. We will also confront the dangers of such a world, a planet where wildfires could rage with an ferocity and intensity almost unimaginable today, creating a global ecosystem perpetually living on the edge of a conflagration. Finally, we will trace the inevitable collapse of this oxygen-rich paradise. The great cove-forming swamps began to vanish, the continents shifted and crashed together in monumental collisions, and the global climate swung violently. The delicate pump that had been siphoning carbon out of the atmosphere and burying it in the ground faltered and stopped. The oxygen levels began their long, precipitous decline, bringing an end to the age of giants and setting the stage for the world we know today. The legacy of that time, however, is buried deep beneath our feet, in the black seams of coal that contained the stored solar energy of those long-lost hyperoxic forests. So, prepare to take a journey deep into time, to a world that was both familiar and utterly alien, a world shaped, defined, and ultimately threatened by the very air it breathed. This is the story of what 35% oxygen did to life on Earth. To truly appreciate the anomaly of 35% oxygen, we must first understand the nature of Earth's atmosphere and how it became the life-giving envelope it is today. Our air is not a static, primordial gift. It is a dynamic, ever-changing product of planetary processes and biological activity. It is, in a very real sense, an extension of the biosphere itself, Earth's first atmosphere, shortly after its formation, some 4.5 billion years ago, was a thin veil of hydrogen and helium, leftover gases from the solar nebula. This primordial shroud was quickly stripped away by the solar wind and the planet's own still molten heat. The second atmosphere emerged from within the planet itself, through the intense volcanic outgassing that characterized the Hadean and early Archean epoch. This was a toxic soup to modern life, a thick, hazy mixture of water vapor, carbon dioxide, nitrogen, methane, ammonia, sulfur dioxide, and hydrogen chloride. There was not a single trace of free oxygen. This was a reducing atmosphere, chemically primed to donate electrons, not accept them. For life to arise in such an environment, it had to be anaerobic life that did not require oxygen and, in fact, found it poisonous. The earliest life forms, simple prokaryotic cells, thrived in this chemical stew, deriving energy from fermentation and chemical reactions like methanogenesis and sulfate reduction. For over 1 billion years, this was the status quo. Then, a revolution began. A group of microbes, the cyanobacteria, evolved a miraculous trick: photosynthesis. Using the energy of sunlight, they could split water molecules, HO, and use the hydrogen to combine with carbon dioxide, CO2, form organic matter for their own growth. The waste product of this revolutionary process was free, gaseous oxygen. Initially, this oxygen did not accumulate in the air. It was a highly reactive poison to the anaerobic life that dominated the planet, and it was quickly mopped up by the environment. It oxidized, dissolved iron in the oceans, precipitating out as vast layers of banded iron formations, rusty red sedimentary rocks that today provide us with most of the world's iron ore. It oxidized rocks on the seafloor and continents. For millions of years, the cyanobacteria's pollution was being efficiently neutralized, but eventually, around 2.4 billion years ago, the planet's capacity to absorb this reactive waste was exhausted. The chemical sinks were full. Oxygen began to leak into the atmosphere. This was the Great Oxidation Event GO, arguably the most significant environmental catastrophe in Earth's history. For the anaerobic biosphere, it was an apocalypse. Oxygen was a deadly toxin, and it poisoned vast swathes of microbial life, driving them into the only refuges that remained: anaerobic muds, deep ocean waters, and subterranean environments. The world was forever changed. This new oxygenated atmosphere allowed for the evolution of a new kind of life: aerobic organisms. These cells, through the miracle of aerobic respiration, learned to not just tolerate oxygen, but to use it. They developed mitochondria, tiny power plants that could use oxygen to burn food molecules completely, extracting far more energy in the form of ATP than anaerobic processes ever could. This energy bonanza was the fundamental prerequisite for all complex life. The high energy yield of aerobic respiration made it possible to support larger sizes, more moving parts, and more complex behaviors. Every animal, every plant, every fungus you see today is a descendant of those early organisms that learned to turn a poison into power. For the next 1.5 billion years, oxygen levels fluctuated, but generally remained well below modern levels. The balance was delicate. Photosynthesis produced oxygen, but respiration and decay consumed it, as organisms and their decomposers broke down organic matter, recombining its carbon with oxygen to form CO once more. It was a nearly closed loop. For oxygen to accumulate, something had to break the loop. Organic carbon, produced by photosynthesis, had to be buried in sediments faster than it could be decomposed and recycled. This process, the sequestration of carbon, is the fundamental engine for raising planetary oxygen levels. This sets the stage for our story. The stage was set for a perfect storm of biological innovation and geological circumstance that would push this delicate balance to an extreme, breaking the loop on a monumental scale and flooding the atmosphere with an unprecedented surplus of oxygen. The Carboniferous period was about to begin. The Carboniferous period, spanning from about 359 to 299 million years ago, derives its name from the Latin for coal-bearing, a testament to its most famous legacy. It was during this time that the geological and biological conditions aligned perfectly to create the hyperoxic atmosphere we are exploring. This was not a random event, but the result of a confluence of several critical factors. First, the geological stage. The continents, driven by the relentless motion of plate tectonics, was slowly converging to form the supercontinent of Pangaea. But in the early Carboniferous, this assembly was not yet complete. Much of the landmass was clustered in the tropics, and vast low-lying coastal areas were flooded by warm, shallow seas. This created an ideal geography for the spread of enormous, waterlogged wetlands and swamps. The climate was globally warm and humid, with no polar ice caps, leading to high sea levels and extensive inland seas. This stable, tropical environment was a greenhouse world, perfect for fostering explosive plant growth. Second, and most crucially, was the biological revolution on land. The Devonian period, immediately preceding the Carboniferous, had seen the first plants tentatively colonize the land. By the Carboniferous, this colonization had become a full-scale invasion. The land was greening at a scale never before seen. But these weren't the familiar flowering plants, grasses, and conifers of today. The Carboniferous forests were dominated by a strange and magnificent cast of characters. Giant club masses called lepidodendron and sigillaria, which looked like trees but were more closely related to today's tiny quillworts. Massive tree ferns with fronds the size of small cars, and horsetails known as calamites, which grew as tall as modern pine trees. These plants possessed a key characteristic that made the Carboniferous unique. They evolved a new molecule called lignin. Lignin is a complex polymer that acts as a super-strong glue, providing structural support and allowing plants to grow tall and woody, to tower over their competitors and reach for the sunlight. It is the substance that makes wood woody. For the first time in Earth's history, the planet was covered in true forests of tall, lignin-rich trees. This was the biological breakthrough that would break the carbon cycle. When these giant trees died, they fell into the warm, waterlogged swamps they called home. Herein lay the problem. Lignin was a brand new invention on an evolutionary timescale. The decomposer organisms of the time, primarily fungi and bacteria, had not yet evolved the complex enzymatic machinery needed to break down this tough, resilient molecule. Today, we have white rot fungi and other microbes that are experts at decaying wood, efficiently recycling its carbon back into the atmosphere. But in the Carboniferous, this recycling service did not exist. The result was that the vast majority of this organic carbon, produced in immense quantities by the hyperproductive tropical forests, was not decomposed. Instead of being consumed by microbes and releasing its carbon back as CO, it simply piled up. Fallen trunks, branches, leaves, and spores accumulated in layer upon layer in the anoxic acidic waters of the swamps. These waters, starved of oxygen, further inhibited any decay that might have slowly occurred. This immense pile of undecayed plant matter, under its own weight and over millions of years, was slowly compressed and cooked into the substance we know as coal. This process, photosynthesis on a colossal scale, followed by a failure of decomposition on an equally colossal scale, was the engine of the oxygen crisis. Every molecule of CO that a Carboniferous plant took in and converted into organic matter released a molecule of O as a byproduct. Normally, when that plant died and decayed, the process would reverse. Decomposers would consume the organic matter, using up oxygen and releasing CO. The net effect was zero. But with decay arrested, the reverse reaction never happened. The oxygen that had been released during the plant's growth remained in the atmosphere. The carbon, meanwhile, was buried forever in the geological record. It was a one-way pump. The biosphere was sucking carbon dioxide out of the air and locking it away in the ground at a staggering rate. And with every ton of carbon buried, the atmospheric reservoir of oxygen grew larger and larger. Estimates suggest that the coal seams of the Carboniferous and Permian periods represent the burial of over 100 trillion tons of organic carbon. The corresponding release of oxygen pushed atmospheric levels to their historic peak of around 35%. This was the perfect storm. The right plants, in the right place, warm, wet tropics, at the right time before decomposers could catch up, under the right geological conditions, vast, sinking basins to preserve the organic matter. The planet had accidentally built a machine for producing oxygen, and for tens of millions of years, it ran at full throttle, fundamentally altering the nature of the air that every living thing depended on. A world with 35% oxygen is not just a world with more of the same air. It is a fundamentally different chemical environment. This hyperoxic atmosphere imposed a new set of physical rules and constraints. driving evolution in strange and spectacular directions. The most famous and visually striking consequence was gigantism, particularly among the arthropods, but the effects ran far deeper, influencing physiology, metabolism, and the very balance of life. Let us start with the giants. The reason arthropods, insects, arachnids, millipedes were so profoundly affected lies in their basic body plan. Unlike vertebrates who use a centralized lung-based system actively pumped by a heart to distribute oxygen, arthropods rely on a passive respiratory system. They have a network of tiny tubes called trachea that pipe air directly to their tissues. Oxygen diffuses through these tubes, and the efficiency of this diffusion is governed by simple physics, specifically Fick's law of diffusion. The rate of diffusion is proportional to the concentration gradient of the gas. In a 35% oxygen atmosphere, that gradient is much, much steeper than in our 21% world. Oxygen literally forces its way deeper and more efficiently into their bodies. This solved a major physiological constraint. In low oxygen, diffusion is slow, limiting the size an arthropod can attain, because oxygen cannot penetrate to the center of a large body quickly enough. But with supercharged diffusion, that size limit was dramatically lifted. Arthropods could grow to dimensions that would be physiologically impossible today. The skies of the Carboniferous were patrolled by Meganeura, a griffinfly, a relative of, but not a true, dragonfly, with a wingspan that could reach an astonishing 70 centimeters, over 2 feet, from wingtip to wingtip. This was a predator the size of a modern hawk, a buzzing, darting aerial acrobat that likely preyed on other large insects, and perhaps even small amphibians. Its compound eyes provided exceptional vision, and its powerful flight muscles, super-oxygenated by the rich air, gave it incredible speed and maneuverability. On the forest floor, the humid undergrowth rustled with the passage of Arthropleura, a giant millipede that could grow over 2.5 meters, 8 feet long, and half a meter wide. This was the largest land invertebrate of all time, a gentle giant that likely fed on rotting vegetation and spores, its segmented body a living conveyor belt moving through the litter of the coal forests. The high oxygen levels not only allowed its immense size, but also reduced the risk of desiccation, as its spiracles, the openings to its tracheal system, did not need to be as wide open to obtain sufficient oxygen, thus losing less water. Scorpions like Pulmonoscorpius reached the length of a house cat, and spiders were correspondingly large. This gigantism was not a quirky sideshow. It was a direct and inevitable consequence of the physics of gas diffusion in a hyperoxic environment. But the effects extended beyond mere size. The high oxygen levels lowered the metabolic cost of activity. Movement, growth, and reproduction all became more energetically affordable. This likely led to more active predators, more evasive prey, and an overall intensification of the arms race between species. For the first vertebrates firmly established on land, the early amphibians, this may have been a mixed blessing. Their simple, inefficient lungs would have found oxygen absorption easier, potentially supporting more active lifestyles. But they were also living in a world of nightmare predators, where a misplaced step could mean being snatched by a giant dragonfly or stung by a scorpion the size of a terrier. Furthermore, high oxygen is a double-edged sword. While it powers efficient metabolism, it is also a potent toxin. Reactive oxygen species, free radicals, are destructive byproducts of metabolism that can damage DNA and proteins. Life in the Carboniferous would have had to evolve enhanced antioxidant systems to mitigate this cellular damage. The high oxygen atmosphere may have also influenced the evolution of the amniotic egg in reptiles, which was beginning to appear at this time. The shell of this egg is permeable to gases, but must also protect the embryo from external threats. In a hyperoxic world, protecting the developing embryo from oxygen toxicity may have been a significant selective pressure, driving the refinement of this revolutionary structure that finally freed vertebrates from the need to lay their eggs in water. The Carboniferous was not, therefore, a simplistic age of giants. It was a complex high-energy ecosystem where the very chemistry of the air supercharged metabolism, lifted ancient physiological constraints, and created both extraordinary opportunities and terrifying new challenges for every form of life that drew breath. If the high oxygen content of the Carboniferous atmosphere supercharged life, it also supercharged destruction. Two fundamental natural processes, fire and decay, were transformed under the influence of 35% oxygen. creating a world that was both a preserver of carbon and a tinderbox waiting for a spark. Let us first consider fire. Combustion is a chemical reaction between a fuel and an oxidizer, oxygen, that releases heat and light. The concentration of the oxidizer is a critical factor. In our modern atmosphere, a fuel like a piece of paper or a dry leaf needs to be heated to its ignition temperature, around 233 degrees Celsius, 451 Fahrenheit, to catch fire. In a 35% oxygen atmosphere, the rules change dramatically. The ignition temperature of materials plummets. Experiments have shown that in 35% oxygen, common materials like paper can ignite at temperatures dozens of degrees lower than in 21% oxygen. But more importantly, once a fire starts, it behaves entirely differently. The fire burns hotter, faster, and more completely. The rate of energy release is vastly increased. A lightning strike that in our world might char a single tree could, in the Carboniferous, explode into a raging inferno almost instantaneously. These would not be the slow-burning ground fires or controlled canopy fires we see today. They would be intense, catastrophic crown fires that would race through the forest canopy at terrifying speeds, consuming everything in their path. The Carboniferous world was therefore living on a knife's edge. Its very nature promoted fire. It was full of fuel in the form of dense, dry in the upper canopy vegetation. The frequent thunderstorms provided a constant source of ignition, and the air itself was primed for conflagration. Evidence for this is found in the fossil record itself. Cold balls, petrified pockets of peat from Carboniferous swamp sand, fossilized charcoal called fusane are incredibly common. The forests burned. They burned often, and they burned ferociously. This created a powerful feedback loop. Major fires would kill vast swathes of vegetation, creating even more downed fuel. When the rains returned, this charred debris would be washed into the swamps, where its already carbonized state made it even more resistant to decay, thus promoting its preservation and contributing further to the carbon burial pump. Fire, paradoxically, helped create the conditions that sustained the high-oxygen world that made such intense fires possible. The second transformed process was decomposition. As discussed, the key to the oxygen spike was the failure of decay, specifically the inability of organisms to break down lignin, but the high oxygen levels themselves would have further complicated decomposition. While we might assume that more oxygen would aid aerobic decomposers, the opposite can be true at extreme concentrations. Hyperoxia can be toxic to many microbes and fungi, inhibiting their growth and metabolic functions. The very abundance of the element they needed to survive may have become a limiting factor, further slowing the rate at which they could break down the mountains of fallen wood. This combination inefficient biological decay, combined with frequent intense fires that pre-charred organic matter, created a preservation bias of epic proportions. The Carboniferous ecosystem was uniquely terrible at recycling itself. It was a world of immense productivity, but also of immense waste. Life was creating organic matter far faster than the processes of rot and decay could possibly handle. The surplus was simply dumped into the geological bin, piling up in waterlogged graveyards that would become the coal measures that fueled the Industrial Revolution 300 million years later. This environment would have also had a peculiar smell. Without efficient decay, the sour methane-laden odor of peat bogs would have been pervasive. The air might have been tinged with the constant, faint smell of smoke from distant fires. It was a world of vibrant, steamy green life, built upon a foundation of black, preserved death. A world where the air that gave life to monstrous insects also empowered the flames that could reduce entire forests to charcoal in a matter of hours. It was a system of fierce and unsustainable extremes. The Carboniferous oxygen paradise was not destined to last. No geological period is permanent, and the specific confluence of conditions that created the hyperoxic atmosphere began to unravel, leading to a long, precipitous decline in oxygen levels. The collapse of this world was as complex as its creation, driven by a combination of biological evolution, climatic shift, and monumental geological forces. The first crack in the foundation was biological. You cannot introduce a limitless food source like hundreds of millions of years worth of stored wood without something eventually evolving to exploit it. Towards the end of the Carboniferous and into the Permian, fungi finally caught up. A group of fungi known as white rot, which is dominant today, evolved the necessary enzymatic toolkit to break down lignin. The key invention was an enzyme called lignin peroxidase, a molecular marvel capable of dismantling the tough polymer into digestible components. This was a revolution in recycling. The great piles of wood that had accumulated for eons now had a consumer. The carbon that had been buried for millions of years began to be unlocked and fed back into the active carbon cycle. As these new decomposers spread, the efficiency of carbon burial plummeted. The one-way pump that had been adding oxygen to the atmosphere began to sputter. Oxygen that was being produced by new photosynthesis was now being consumed at a much higher rate by the decomposition of both contemporary plant matter and the vast ancient stores that were now being exposed and broken down. The net production of oxygen slowed, halted, and then reversed. The second major factor was geological and climatic. The slowdowns of the continents continued. The formation of the supercontinent Pangaea accelerated as landmasses collided and fused together. This had two critical consequences. First, the vast low-lying tropical coastal regions that had hosted the coal-forming swamps began to shrink. The interior of Pangaea became a single, massive continent, which led to a much more arid and seasonal climate across large parts of the world. The warm, wet, stable conditions that were perfect for swamp forests gave way to drier, more variable environments. The coal swamps retreated, and with them died the primary engine of carbon burial. Second, the immense mountain-building events orogenies that occurred as continents collided, such as the formation of the Appalachians and the Ural Mountains, exposed vast amounts of fresh rock to the atmosphere. This accelerated a process called silicate weathering. Rainwater, slightly acidic from dissolved CO, reacts with silicate rocks in a chemical process that draws carbon dioxide out of the atmosphere and eventually deposits it as carbonate minerals on the ocean floor. This is a long-term carbon sink. While not directly consuming oxygen, a drop in CO can indirectly affect the oxygen cycle by potentially reducing the rate of photosynthesis globally. Though the effects are complex and debated, the planet was also tilting towards an ice age. The movement of Gondwana, the southern part of Pangaea, over the South Pole, led to the formation of massive glaciers. Global temperatures fell, sea levels dropped, and the climate became more extreme. This further stressed the tropical ecosystems that had dominated the Carboniferous. The combination of these factors was devastating to the high-oxygen world. The biological innovation of wood-decaying fungi broke the carbon burial pump. The geological changes destroyed the ideal habitat for that pump to operate. The result was a long and dramatic crash in atmospheric oxygen levels. From its peak of 35%, it likely fell to around 15%, or even lower by the end of the Permian period, a drop that represented a halving of the oxygen content of the air. This decline had profound consequences for life. The age of giant arthropods came to an abrupt end. Their tracheal systems, evolved for hyperoxia, could not function in the new thin air. They faced suffocation on a planetary scale. The giant griffinflies, the massive millipedes, and the huge spiders vanished, their lineages either going extinct or shrinking back to the sizes we are familiar with today. The world was becoming tougher, drier, colder, and crucially, it was running out of breathable air. This atmospheric shift set the stage for the greatest catastrophe ever to befall life on Earth. The Permian-Triassic extinction event, where up to 96% of all marine species and 70% of terrestrial vertebrate species were wiped out, while the causes of the Great Dying were multifaceted, involving massive Siberian volcanic eruptions, methane release, and ocean anoxia. The pre-existing decline in oxygen levels likely stressed global ecosystems to a breaking point, making them uniquely vulnerable to the final cataclysm. The long reign of the Carboniferous forests was over. The world that emerged from the Permian-Triassic extinction was a new one, dominated by different plants and animals, and breathing different air. The age of oxygen had passed. The Carboniferous period did not simply end. Its legacy is woven into the very fabric of our modern world. From the energy that powers our civilizations, to the air we breathe, and the biological communities that surround us, the echoes of that hyperoxic time resonate hundreds of millions of years later. The most obvious legacy is coal. The vast, undecayed remains of those Carboniferous and Permian forests were buried under immense pressure and heat over geological time, transforming into the dense, black rock we mine today. This coal, the fossilized sunshine of a lost world, became the primary fuel of the Industrial Revolution. It powered the steam engines, forged the steel, and generated the electricity that built the modern world. In a profound irony, we are now burning this stored carbon at a rate that dwarfs the original burial process, releasing billions of tons of carbon dioxide back into the atmosphere over centuries instead of millions of years, dramatically altering the climate of the planet in the process. Our modern climate crisis is, in a very real sense, the rapid, uncontrolled reversal of the Carboniferous carbon cycle. The second legacy is the air we breathe. The oxygen we depend on every second is not a permanent fixture. It is a biological product, and its level has fluctuated wildly over time. The current level of 21% is not a special, predetermined number. It is simply the current equilibrium point in the long-term carbon cycle. Many scientists believe that the Carboniferous oxygen peak was a unique, non-repeatable event. The evolution of lignin was a one-time innovation that caught the decomposer community off guard. Now that efficient decomposers exist, it is unlikely that such a massive imbalance could ever occur again. Our atmosphere has settled into a relatively stable balance, but it is a balance maintained by biology, and one that is now being profoundly disrupted by human activity. The third legacy is biological. The end of the Age of Giants cleared ecological space for other organisms. The vertebrates, specifically the reptiles and later the mammals, which were not as constrained by passive respiratory systems, were able to diversify and eventually dominate the land. The Permian-Triassic extinction, while horrific, paved the way for the age of dinosaurs and, ultimately, the rise of mammals. The strategies for dealing with oxygen, from the sophisticated four-chambered hearts of birds and mammals to the efficient respiratory systems of insects, were all refined in the shadow of the Carboniferous rise and fall. Furthermore, the Carboniferous represents a powerful case study in the deep interconnections between life and its environment. The Gaia hypothesis, which posits that life actively regulates and maintains the conditions of the planet, finds a compelling, if complex, example here. Life in the form of lignin-producing trees changed the atmosphere dramatically. That change in turn drove evolution, selecting for gigantism and new physiological adaptations. And then, life in the form of wood-decaying fungi changed the atmosphere again, bringing the oxygen spike to an end. It demonstrates that the planet is not a static stage on which evolution plays out. The stage itself is being constantly rebuilt and remodeled by the players. Finally, the story of the Carboniferous oxygen peak serves as a cautionary tale about the power of chemistry. A change in the composition of the air by just a few percentage points can remake the world, driving some life forms to extinction and propelling others to dominance. It reminds us that the seemingly immutable nature of our environment is an illusion. The air is fragile. It is a product of life, and it can be taken away by changes to the biological processes that sustain it. As we now engage in a global-scale experiment of our own pumping carbon that was buried over millions of years back into the atmosphere in a geological instant, we would do well to remember the lesson of the Carboniferous. The world can be utterly transformed by a change in the air. Our journey back to the world of 35% oxygen is now complete. We have traveled from the first photosynthetic bacteria that poisoned their own world with oxygen, to the vast, steamy coal forests where trees grew tall on a substance nothing could rot. We have witnessed the terrifying and magnificent creatures that soared and scurried through those hyperoxic jungles, supercharged by the rich air. We have felt the heat of the superfires that routinely ravaged the landscape and understood the strange chemistry that preserved so much carbon and built the oxygen-rich world. And we have seen it all crumble, brought down by the evolution of a humble fungus and the relentless drift of continents. This story is more than a curious chapter in a paleontology textbook. It is a profound demonstration of the dynamic and intimate relationship between life and the planet it inhabits. The Earth is not a passive rock orbiting the Sun. It is a complex, self-regulating system where the atmosphere, the rocks, the oceans, and life itself are all deeply intertwined in a constant, feedback-driven dance. The Carboniferous is perhaps the most extreme example of life seizing control of the planetary thermostat and air mixture, albeit unintentionally, and holding it there for millions of years. It also reshapes our understanding of what is normal. We think of our 21% oxygen atmosphere as standard, but Earth's history shows that this is merely a snapshot. a temporary equilibrium in a 4.5 billion year saga of chemical change. The planet has been many different worlds: a reducing world of iron oceans, a snowball world encased in ice, a greenhouse world of crocodiles in the Arctic, and a superoxygenated world of giant insects. This perspective is humbling. It tells us that change is the only constant, as we face an uncertain climatic future, driven by our own alteration of the carbon cycle. The lessons of the Carboniferous are more relevant than ever. They teach us about the power of feedback loops, the unpredictability of biological innovation, and the sheer scale of change that is possible when planetary systems are pushed out of balance. The Carboniferous shows us that life is resilient and will find a way, but it also shows us that the world that emerges from a period of extreme change can be utterly unlike the one that came before. So, the next time you take a deep breath of fresh air, remember that it carries the legacy of ancient forests and forgotten giants. The oxygen molecules that fuel your cells once fueled the flight of a dragonfly with a wingspan like an eagle. The air is a repository of deep time, a connection to a world that was both marvelous and terrifyingly alien, and it reminds us that we, too, are part of this endless dance, living on a planet that is always, inevitably, in a state of becoming something new. While the giant arthropods and towering trees capture our imagination, the true masters of the Carboniferous world, as in all periods of Earth's history, were the microbes. Bacteria, archaea, and protists formed the unseen foundation of the entire ecosystem, and the high oxygen environment presented them with both a profound challenge and a unique opportunity. Their story is one of biochemical innovation, niche specialization, and a constant struggle for survival in a world saturated with a toxic element. For anaerobic microbes, the rise to 35% oxygen was a continuing nightmare. The Great Oxidation Event had forced them into refugia billions of years earlier, but the Carboniferous atmosphere was even more hostile. These ancient lineages, which still performed essential functions like methanogenesis and sulfate reduction, were pushed even further into the margins. Their worlds shrank to the deepest, most anoxic layers of swamp muck, to the guts of large animals where oxygen could be excluded, and to deep subterranean environments. The reign of their ancestors was a distant memory, and they persisted in a planet that had become, from their perspective, a globally toxic spill. For aerobic microbes, however, it was a time of plenty. Oxygen was their energy currency, and the atmosphere was a boundless bank. Cyanobacteria continued their timeless work in the oceans and freshwater swamps, their photosynthesis now operating in an environment where oxygen, their waste product, could diffuse away rapidly. But the real action was on land, in the soils, and within the litter of the great forests. The high oxygen levels supercharged decomposition for the materials that could be decomposed. Bacteria and fungi that fed on sugars, cellulose, and other non-lignin components of plants would have had incredibly high metabolic rates. The breakdown of softer plant tissues, dead animals, and animal waste would have been extremely rapid, recycling nutrients back into the ecosystem at a ferocious pace. This helped fuel the immense productivity of the forests, creating a feedback loop of growth and rapid recycling of everything except the stubborn lignin. This environment likely drove an evolutionary arms race among decomposers. With such an abundance of energy available, competition for the vast resources of undecayed plant matter would have been intense. This pressure is what ultimately led to the evolutionary breakthrough toward the end of the period: the ability to break down lignin. The first fungus that mutated a primitive enzyme capable of attacking the lignin polymer would have found itself sitting atop a limitless food supply, triggering an evolutionary revolution. Furthermore, the high oxygen levels would have influenced the nitrogen cycle. Nitrogen fixation, the process of converting inert atmospheric nitrogen N into biologically usable ammonia, is an energy-intensive process that can be facilitated by certain bacteria. Some nitrogen-fixing bacteria are aerobic, and the abundant oxygen may have supported more efficient nitrogen fixation, further fertilizing the ecosystems and contributing to the lush growth. However, other parts of the cycle, like denitrification, the conversion of nitrates back to N, are performed by anaerobes, which would have been suppressed. The overall effect on global nitrogen budgets would have been complex, tilting the scales toward the accumulation of bioavailable nitrogen in the environment. In the oceans, the picture was different. While the atmosphere was hyperoxic, the oceans could still host vast anoxic zones, particularly in deeper, stagnant basins. The warm climate reduced ocean circulation, and the high productivity in surface waters led to huge amounts of organic matter sinking into the depths, where its decomposition by bacteria would consume all available oxygen. In these dark, oxygen-free zones, anaerobic microbes thrived, producing hydrogen sulfide as a byproduct. These eosinic conditions created deadly pockets of toxicity that would have been impassable barriers for most complex marine life. Thus, the microbial world of the Carboniferous was a world of stark contrasts: hyper-efficiency and fierce competition in oxygen-rich soils, and desperate survival in marginalized anaerobic refugia. The bacteria and fungi were not just passengers in this world, they were the essential engineers of its chemistry. They mediated the cycles of carbon, nitrogen, and sulfur that made the world function, and it was their eventual evolutionary innovation that would bring the era of high oxygen to a close, proving that the smallest organisms can ultimately dictate the fate of the largest. While the arthropods were exploiting the physical advantages of hyperoxia through gigantism, the vertebrates of the Carboniferous were on a different evolutionary path. For them, the high oxygen atmosphere was not a key to unprecedented size, but rather a facilitator for one of the most important transitions in the history of life: the conquest of the land and the break from water. The vertebrates responded not by becoming giants, but by becoming smarter, tougher, and finally, truly free. The dominant land vertebrates of the early Carboniferous were the amphibians, descendants of lobefin fish like Tiktaalik. These animals, such as the crocodile-like Eogyrinus or the more salamander-like Dinrepetin, were the first vertebrates to properly establish a foothold on land. But it was a tenuous foothold. Their anatomy was a compromise. They had legs instead of fins, but their limbs were splayed out to the side, making for a slow, inefficient, sprawling gait. Most critically, they were still tethered to the water. They had to return to ponds and streams to lay their soft, gelatinous eggs, which would hatch into aquatic larvae tadpoles, that would later metamorphose into adults. The high-oxygen environment benefited these early pioneers. Amphibians breathed not only with simple, inefficient lungs, but also through their moist skin cutaneous respiration. The steep concentration gradient of oxygen in the air meant that cutaneous respiration became a highly effective method of gas exchange. Oxygen could diffuse more easily through their skin into their blood, supplementing their lung-based breathing and supporting a more active metabolism. This may have allowed them to grow larger and more robust than would have been possible in a lower oxygen world. They were the apex predators of their terrestrial ecosystems, filling niches that would later be taken by reptiles and mammals, preying on large insects, fish, and each other. But the real story of vertebrate evolution in the Carboniferous is the story of the amniotic egg. The high oxygen atmosphere may have played a crucial, albeit indirect, role in its evolution. The first amniotes, small, lizard-like animals, such as Hylonomus, found fossilized inside hollowed-out lepidodendron stumps, were evolving in the shadows of their amphibian cousins. Their key innovation was the amniotic egg, a self-contained life support system with a protective shell, a series of membranes, the amnion, chorion, and allantois, that managed waste and facilitated gas exchange, and a yolk sac to nourish the developing embryo. This egg was nothing short of revolutionary. It freed the vertebrates from their final tether to the water. They could now lay their eggs on dry land, in hidden nests, away from the predators teeming in the water. This opened up vast new inland territories that were inaccessible to amphibians. And here is where oxygen may have been critical. A developing embryo is highly vulnerable to oxygen-free radicals, which can cause catastrophic damage to its growing tissues. In a world of 35% oxygen, this threat would be magnified. The shell and membranes of the amniotic egg did not just allow oxygen in, they also regulated its passage. They provided a controlled, protective environment that could supply the embryo with enough oxygen to develop, while simultaneously shielding it from the toxic effects of the hyperoxic atmosphere outside. It was a perfect adaptation to the environmental conditions of the time. The amniotic egg was, in a sense, a personal miniature atmosphere for the embryo, buffering it from the extremes of the outside world. This adaptation allowed the amniotes to diversify. They split into two major lineages: the synapsids, which would eventually lead to mammals, and the sauropsids, which would lead to reptiles, dinosaurs, and birds. Initially small and insectivorous, These first amniotes were the underdogs, but they held the key to the future. They were more resilient, more adaptable and free to explore new ecological niches. The Carboniferous era, therefore, did not just make giant bugs, it helped forge the evolutionary tool, the amniotic egg, that would eventually allow vertebrates to dominate the planet for the next 300 million years through every climate change and extinction event to come. The amphibians had their reign in the oxygen-rich swamps, but the future belonged to the animals that could carry their own watery world with them, in an egg, anywhere on land. While the giant arthropods and towering trees capture our imagination, the true masters of the Carboniferous world, as in all periods of Earth's history, were the microbes. Bacteria, archaea, and protists formed the unseen foundation of the entire ecosystem, and the high oxygen environment presented them with both a profound challenge and a unique opportunity. Their story is one of biochemical innovation, niche specialization, and a constant struggle for survival in a world saturated with a toxic element. For anaerobic microbes, the rise to 35% oxygen was a continuing nightmare. The Great Oxidation Event had forced them into refugia billions of years earlier, but the Carboniferous atmosphere was even more hostile. These ancient lineages, which still performed essential functions like methanogenesis and sulfate reduction, were pushed even further into the margins. Their worlds shrank to the deepest, most anoxic layers of swamp muck, to the guts of large animals where oxygen could be excluded, and to deep subterranean environments. The reign of their ancestors was a distant memory, and they persisted in a planet that had become, from their perspective, a globally toxic spill. For aerobic microbes, however, it was a time of plenty. Oxygen was their energy currency, and the atmosphere was a boundless bank. Cyanobacteria continued their timeless work in the oceans and freshwater swamps, their photosynthesis now operating in an environment where oxygen, their waste product, could diffuse away rapidly. But the real action was on land, in the soils, and within the litter of the great forests. The high oxygen levels supercharged decomposition for the materials that could be decomposed. Bacteria and fungi that fed on sugars, cellulose, and other non-lignin components of plants would have had incredibly high metabolic rates. The breakdown of softer plant tissues, dead animals, and animal waste would have been extremely rapid, recycling nutrients back into the ecosystem at a ferocious pace. This helped fuel the immense productivity of the forests, creating a feedback loop of growth and rapid recycling of everything except the stubborn lignin. This environment likely drove an evolutionary arms race among decomposers. With such an abundance of energy available, competition for the vast resources of undecayed plant matter would have been intense. This pressure is what ultimately led to the evolutionary breakthrough toward the end of the period: the ability to break down lignin. The first fungus that mutated a primitive enzyme capable of attacking the lignin polymer would have found itself sitting atop a limitless food supply, triggering an evolutionary revolution. Furthermore, the high oxygen levels would have influenced the nitrogen cycle. Nitrogen fixation, the process of converting inert atmospheric nitrogen N into biologically usable ammonia, is an energy-intensive process that can be facilitated by certain bacteria. Some nitrogen-fixing bacteria are aerobic, and the abundant oxygen may have supported more efficient nitrogen fixation, further fertilizing the ecosystems and contributing to the lush growth. However, other parts of the cycle, like denitrification, the conversion of nitrates back to N, are performed by anaerobes, which would have been suppressed. The overall effect on global nitrogen budgets would have been complex, tilting the scales toward the accumulation of bioavailable nitrogen in the environment. In the oceans, the picture was different. While the atmosphere was hyperoxic, the oceans could still host vast anoxic zones, particularly in deeper, stagnant basins. The warm climate reduced ocean circulation, and the high productivity in surface waters led to huge amounts of organic matter sinking into the depths, where its decomposition by bacteria would consume all available oxygen. In these dark, oxygen-free zones, anaerobic microbes thrived, producing hydrogen sulfide as a byproduct. These eugenic conditions created deadly pockets of toxicity that would have been impassable barriers for most complex marine life. Thus, the microbial world of the Carboniferous was a world of stark contrasts: hyper-efficiency and fierce competition in oxygen-rich soils, and desperate survival in marginalized anaerobic refugia. The bacteria and fungi were not just passengers in this world. They were the essential engineers of its chemistry. They mediated the cycles of carbon, nitrogen, and sulfur that made the world function, and it was their eventual evolutionary innovation that would bring the era of high oxygen to a close, proving that the smallest organisms can ultimately dictate the fate of the largest. While the arthropods were exploiting the physical advantages of hyperoxia through gigantism, the vertebrates of the Carboniferous were on a different evolutionary path. For them, the high oxygen atmosphere was not a key to unprecedented size, but rather a facilitator for one of the most important transitions in the history of life, the conquest of the land and the break from water. The vertebrates responded not by becoming giants, but by becoming smarter, tougher, and finally, truly free. The dominant land vertebrates of the early Carboniferous were the amphibians, descendants of lobefin fish like Tiktaalik. These animals, such as the crocodile-like Eogyrinus or the more salamander-like Dinrepetin, were the first vertebrates to properly establish a foothold on land. But it was a tenuous foothold. Their anatomy was a compromise. They had legs instead of fins, but their limbs were splayed out to the side, making for a slow, inefficient, sprawling gait. Most critically, they were still tethered to the water. They had to return to ponds and streams to lay their soft, gelatinous eggs, which would hatch into aquatic larvae tadpoles, that would later metamorphose into adults. The high oxygen environment benefited these early pioneers. Amphibians breathe not only with simple, inefficient lungs, but also through their moist skin cutaneous respiration. The steep concentration gradient of oxygen in the air meant that cutaneous respiration became a highly effective method of gas exchange. Oxygen could diffuse more easily through their skin into their blood, supplementing their lung-based breathing and supporting a more active metabolism. This may have allowed them to grow larger and more robust than would have been possible in a lower oxygen world. They were the apex predators of their terrestrial ecosystems, filling niches that would later be taken by reptiles and mammals, preying on large insects, fish, and each other. But the real story of vertebrate evolution in the Carboniferous is the story of the amniotic egg. The high oxygen atmosphere may have played a crucial, albeit indirect, role in its evolution. The first amniotes, small, lizard-like animals, such as Hylonomus, found fossilized inside hollowed-out lepidodendron stumps, were evolving in the shadows of their amphibian cousins. Their key innovation was the amniotic egg, a self-contained life support system with a protective shell, a series of membranes, the amnion, chorion, and allantois, that managed waste and facilitated gas exchange, and a yolk sac to nourish the developing embryo. This egg was nothing short of revolutionary. It freed the vertebrates from their final tether to the water. They could now lay their eggs on dry land, in hidden nests, away from the predators teeming in the water. This opened up vast new inland territories that were inaccessible to amphibians. And here is where oxygen may have been critical. A developing embryo is highly vulnerable to oxygen-free radicals, which can cause catastrophic damage to its growing tissues. In a world of 35% oxygen, this threat would be magnified. The shell and membranes of the amniotic egg did not just allow oxygen in, they also regulated its passage. They provided a controlled protective environment that could supply the embryo with enough oxygen to develop, while simultaneously shielding it from the toxic effects of the hyperoxic atmosphere outside. It was a perfect adaptation to the environmental conditions of the time. The amniotic egg was, in a sense, a personal miniature atmosphere for the embryo, buffering it from the extremes of the outside world. This adaptation allowed the amniotes to diversify. They split into two major lineages: the synapsids, which would eventually lead to mammals, and the sauropsids, which would lead to reptiles, dinosaurs, and birds. Initially small and insectivorous, these first amniotes were the underdogs, but they held the key to the future. They were more resilient, more adaptable, and free to explore new ecological niches. The Carboniferous era, therefore, did not just make giant bugs, it helped forge the evolutionary tool, the amniotic egg, that would eventually allow vertebrates to dominate the planet for the next 300 million years through every climate change and extinction event to come. The amphibians had their reign in the oxygen-rich swamps, but the future belonged to the animals that could carry their own watery world with them, in an egg, anywhere on land. To walk through a Carboniferous forest would be to experience a world of breathtaking scale and alien beauty. This was not a forest in any modern sense. It was a botanical empire dominated by lineages that are now extinct or relegated to minor, humble roles in our ecosystems. The architecture of the forest, its textures, its colors, and even its silence, broken only by the wind and the buzz of giant insects, would be profoundly strange to us. The kings of this empire were the lycopsids, or scaled trees Lepidodendron and Sigillaria. These were not trees as we know them. They are more closely related to today's small club masses, but they evolved a tree-like form through convergent evolution. A lepidodendron could soar to heights of 50 meters, 160 feet, or more. Its trunk was mostly a long, straight, pillar-like structure that was surprisingly narrow for its height. It did not have thick swirling growth rings like a oak or a pine. Instead, its bark was patterned with diamond-shaped leaf scars that arranged in a spiral pattern, giving the trunk a reptilian or scaly appearance, hence the name scale tree. At the very top of this immense pillar, after perhaps 30 meters of bare trunk, would burst a mere umbrella of branches, themselves covered in long, narrow leaves. The tree's growth strategy was live fast, die young. It grew with astonishing speed to reach the canopy, reproduced once with a massive cone-like structure at its tip, and then died. Its root system was surprisingly shallow and weak, for such a giant, more like a rhizomatous mat than a deep taproot, which is why we find vast fields of these giants toppled over in the fossil record, their fall preserved in the mud. Alongside the lycopsids stood the sphenopsids. The horsetails, their representative calamites, looked like a giant version of its modern descendant, but grew to 20 meters tall. It had a jointed bamboo-like trunk with whorls of branches and leaves at each node. In the wet understory, smaller tree ferns would have spread their elegant fronds, their trunks covered in a dense mat of dead leaf bases and aerial roots. The forest floor would have been a spongy, waterlogged mat of decomposing vegetation, mosses, and liverworts. There was no grass. There were no flowers. The palette would have been a deep, monochromatic green, punctuated by the darker browns of trunks and the bright white of fungus growing on rotting wood. The air would be still, hot, and incredibly humid, filled with the smell of damp decay and the constant drip of moisture from the canopy above. The ecology of this forest was unique. Its incredible productivity was based on a paradox. It was a system that was both hyper-efficient and incredibly wasteful. It was efficient in its rapid growth and its quick recycling of nutrients from soft tissues, but it was wasteful in its inability to process its primary structural material, lignin. This waste was its gift to the future. The structure of the forest also created unique habitats. The tall, straight trunks of lepidodendron created a cathedral-like effect below the canopy. The hollow stumps of fallen trees, revealed by their decay-resistant outer bark, became pitfall traps for animals and perfect nesting sites for small early reptiles like Hylonomus, which are found fossilized within them. This botanical empire was a product of its time, a specific combination of climate, chemistry, and evolutionary history. It was a world without major large vertebrate herbivores. Nothing existed that could chew through the tough, woody trunks or the often toxic leaves. The major herbivores were arthropods, and their feeding damage was likely minimal compared to the browsing of later dinosaurs or mammals. The plants ruled supreme, locked in a competition for light in the steamy, saturated air, building their bodies from carbon dioxide and sunlight, and in the process, accidentally remaking the atmosphere of their entire planet. It was a green world, a silent world, and a world destined for collapse. But for tens of millions of years, it was the most successful and transformative ecosystem the land had ever seen. While the dramatic story of hyperoxia unfolds on land, the aquatic environments of the Carboniferous, the vast coastal swamps, rivers, and the global ocean played an equally crucial role as both participants and regulators in this global chemical drama. They were not separate worlds, but were intimately connected to the atmospheric changes, serving as the engines of carbon burial, the refuges for ancient life, and the habitats for a diverse array of organisms that were both familiar and strange. The starfish of the Carboniferous show were the epicontinental seas. These were shallow, warm seas that flooded the interiors of continents due to the high sea levels from the lack of polar ice caps. They were the cradle of the coal swamps, which thrived along their muddy, low-lying coasts. The chemistry of these seas was critical. As the giant plants died and their remains were washed into these stagnant, waterlogged environments, the water became anoxic, oxygen depleted and acidic. This perfect preservation environment prevented decomposition, allowing the plant matter to accumulate as peat, the precursor to coal. The seas, in effect, provided the burial ground for the carbon that was being extracted from the atmosphere by the forests. Within these swamps and rivers, life was abundant and specialized. The water was warm and rich in nutrients, supporting a huge biomass. Freshwater sharks, such as xenocanthus, patrolled the waterways, along with large armored fish and lungfish. Giant aquatic arthropods, like the sea scorpion Eurypteride, megarock, though its classification is debated, were formidable predators. Amphibians were everywhere, both as predators and prey. The labyrinthodont amphibians, named for the complex, folded structure of their teeth, were the crocodiles of their day, lurking in the murky waters waiting to ambush prey. The oceans themselves presented a different picture. Marine life was recovering from the late Devonian extinction and was thriving, though it would not have looked entirely modern. Coral reefs were building extensive structures, but they were constructed by different organisms than today's reef builders. Instead of the stony corals we know, these reefs were built by bizarre, now extinct organisms like sponges and bryozoans, creating reef mounds that dotted the continental shelves. The cartilaginous fish sharks, rays, and the bony fish rafed and lobe-finned were diversifying rapidly. Sharks, in particular, began their long reign as apex ocean predators. But one of the most iconic marine inhabitants was the crinoid, or sea lily. These animals, related to starfish and sea urchins, looked like beautiful flowers anchored to the seafloor by a long stalk. They lived in such incredible numbers that their skeletal remains form entire limestone formations called crinoidal limestones. However, the high oxygen atmosphere did not necessarily translate to high oxygen in all parts of the ocean. The warm climate led to stratified oceans with poor circulation between the warm, oxygenated surface waters and the cold, deep waters. The high productivity in the surface waters, fueled by nutrients washing off the lush countenance, meant that huge amounts of organic matter sank into the depths. As bacteria decomposed this rain of debris, they consumed the available oxygen, creating vast oxygen minimum zones, OMG, and even completely anoxic conditions in the deep basins. In these dark zones, only anaerobic bacteria and specialized extremophiles could survive. This ocean stratification had another consequence. The anoxic bottom waters prevented the disturbance of buried organic carbon. Once carbon settled into these deep, stagnant graveyards, it was likely to stay there, further contributing to the long-term drawdown of atmospheric CO and the corresponding rise of O. Thus, the aquatic realm was the silent partner to the terrestrial drama. The swamps provided the burial grounds, the rivers transported the carbon, and the stratified oceans locked it away. It was a global system operating in a delicate balance, where life in the water was directly responsible for regulating the air that life on land breathed. The oceans were the final piece of the puzzle, the vast geological repository that made the age of oxygen possible. A 35% oxygen atmosphere is not just a biological stimulus. It is a physical environment with different properties that would have influenced everything from the weather to the color of the sky. To understand the Carboniferous world fully, we must step back and consider the physics and chemistry of its air, the very medium through which life moved, breathed, and sensed its surroundings. First, the density. Earth's atmosphere is composed of roughly 78% nitrogen and 21% oxygen today. Nitrogen molecules, N, are slightly lighter than oxygen molecules. If you replace a significant portion of the nitrogen with the heavier oxygen, the overall molecular weight of the air increases. A 35% oxygen atmosphere would have been denser and heavier than our current air. This has immediate physical consequences. For flying animals, denser air provides more lift. This is a fundamental principle of aerodynamics. For the giant insects like Meganeura, this was a critical advantage. Their wings, which were simple structures without the complex musculature of bird or bat wings, relied on creating vortices and generating lift in a medium that was now more substantial. The dense air made their flight more efficient and less energetically costly, contributing directly to their ability to achieve such immense sizes. It would have been easier to take off, easier to maneuver, and easier to stay aloft. The density would also affect sound. Sound waves travel faster and farther in denser media. The Carboniferous world may have been a surprisingly loud place, The buzzing of insect wings would have been deeper and more resonant. The calls of amphibians, perhaps used for communication and mating, would have carried farther through the thick, humid air. The crash of a falling tree would have boomed like cannon fire. The world would have had a different acoustic texture, filled with low-frequency sounds that propagated efficiently through the dense atmosphere. The chemistry of fire, as discussed, was radically altered. But beyond mere combustion, the high oxygen levels would have accelerated other oxidation reactions. Rusting would occur more rapidly. The weathering of rocks would proceed at a different pace, potentially releasing nutrients into the soil more quickly. Even the metabolism of animals at the cellular level was different. While more energy was available, the risk of oxidative damage was ever present, selecting for more efficient antioxidant systems in all aerobic organisms. The sky itself might have appeared different. Our blue sky is caused by Rayleigh scattering, where molecules in the air scatter shorter blue wavelengths of light more than longer red wavelengths. The composition of the air affects this scattering. An atmosphere with a higher proportion of oxygen molecules might have subtly altered the scattering process. It is possible the sky had a slightly different hue, perhaps a deeper, more intense blue, or even a slight tinge of other colors, due to the different way light interacted with the denser, oxygen-rich air. Sunsets, influenced by the passage of light through more atmosphere, could have been even more spectacular, blazing with intense oranges and reds. Furthermore, the increased density and oxygen content could have influenced weather patterns. A denser atmosphere has a higher heat capacity, meaning it can hold more heat. This could have contributed to the generally warm, stable global climate of the period, reducing extreme temperature fluctuations between day and night. The physics of evaporation and condensation would also operate under different parameters, potentially affecting cloud formation and rainfall patterns. In essence, the air of the Carboniferous was not just food for respiration. It was a different physical medium. It was a thicker, heavier, more reactive soup that shaped the flight of insects, the transmission of sound, the spread of fire, and perhaps even the color of the heavens. Life didn't just breathe this air, it evolved within it, every aspect of its form and function fine-tuned to the unique physics and chemistry of a world that no longer exists. The Carboniferous world was not a static, unchanging hothouse. While it was generally warm and humid on a global scale, it possessed its own rhythms, its own pulse of seasons, climatic shifts, and even the gradual descent into the ice age that would mark its end. Understanding these cycles is key to understanding how the great coal-forming ecosystems functioned and why they eventually faded. The heart of the Carboniferous climate was its stability, driven by geography and greenhouse gases. The concentration of landmasses in the tropics meant that most continents were receiving intense, year-round solar energy. There were no large polar ice caps to create global temperature gradients and drive powerful jet streams. The high levels of carbon dioxide and methane early in the period created a strong greenhouse effect, trapping heat and maintaining globally warm conditions. Sea levels were high, flooding continental interiors and creating the vast, shallow seas that moderated the climate further. Within this warm world, the seasons would have been driven not by temperature, but by precipitation. The Carboniferous likely experienced strong monsoonal cycles. The immense heat over the continental interiors would have drawn moist air in from the surrounding oceans, leading to incredibly wet seasons with daily, torrential downpours that flooded the swamps and fueled explosive plant growth. This would be followed by drier seasons where water levels receded, perhaps concentrating organic matter and even allowing for the possibility of fires, though the ever-present humidity probably kept these in check for much of the period. This cycle of wet and dry was the metronome to which the coal swamps kept time. During the wet seasons, productivity boomed, and the waterlogged conditions were perfect for preserving organic matter. During the slightly drier periods, the fallen vegetation could be exposed and perhaps partially oxidized, but was then quickly buried again with the return of the rains. This pulsating rhythm allowed for the sequential layering of organic material that characterizes coal seams. However, this stability was not to last. The slow, relentless collision of continents to form Pangaea began to change everything. As the supercontinent coalesced, the vast low-lying coastal regions that hosted the coal swamps were squeezed and uplifted. The interior of Pangaea became a single, massive landmass, far from the moderating influence of the ocean. This led to the development of a much more extreme continental climate in the interior. blisteringly hot summers and surprisingly cold winters. The constant, year-round humidity that the swamps depended on began to fail. At the same time, the movement of the southern part of Pangaea Gondwana over the South Pole initiated one of the most severe ice ages in Earth's history. Glaciers began to spread across the polar region. While the tropics remained warm, the global climate system was thrown into turmoil. The immense ice sheets locked up vast quantities of water, causing global sea levels to drop dramatically. This drained the great coastal swamps, exposing them to the air and ending the perfect preservation conditions. The warm, stable, wet world that had fostered the coal forests was breaking apart, replaced by a world of extremes of ice and fire, of deserts and seasonal droughts. This climatic shift is recorded in the rocks. The classic, thick coal seams of the early Carboniferous, the Mississippian, give way in the later Carboniferous, the Pennsylvanian. Two sequences of coal interspersed with layers of sandstone and shale that indicate rivers and floodplains, and even evidence of dry soil formation. By the end of the period, the classic coal swamps were in full retreat, surviving only in refugia. The great pump was slowing down. The pulse of the planet was changing. The steady, humid rhythm of the early Carboniferous was replaced by the erratic, unpredictable beat of a world in climatic transition. This change, more than any other single factor, spelled the end for the hyperoxic atmosphere. The engine of carbon burial was being dismantled by the very geological forces that had helped create it. The story of the Carboniferous hyperoxia is not mere speculation. It is a robust scientific conclusion drawn from multiple, independent lines of evidence. Paleontologists and geochemists are like detectives reconstructing a crime scene from 300 million years ago, and they have gathered a compelling array of clues that point to a world of high oxygen. This evidence comes from the rocks, the fossils, and the very chemistry of ancient materials preserved over eons. The most direct evidence comes from the study of isotopes and ancient gas bubbles. While we don't have samples of ancient air, we have proxies. One of the most powerful methods involves analyzing the ratio of different carbon isotopes, carbon-12 and carbon-13, in sedimentary rocks from the Carboniferous. Photosynthesis preferentially uses the lighter C12 isotope. Therefore, when huge amounts of organic matter rich in C12 are buried and prevented from decaying, the seawater and atmosphere become enriched in the heaviest C13 isotope. This isotopic signature is recorded in limestone and other marine sediments from the period. The scale of the C13 enrichment during the Carboniferous is massive, indicating an unprecedented amount of organic carbon burial, which directly implies a massive release of oxygen. Another method involves studying the oxidation of elements in ancient soils, paleosols. The degree to which iron and other elements are oxidized in fossil soils can provide a rough gauge of the atmospheric oxygen levels under which they formed. Paleosols from the Carboniferous and early Permian show chemical signatures consistent with formation under very high oxygen pressures. Perhaps the most ingenious line of evidence comes from fossilized amber-tree resin. Some studies have analyzed the gas bubbles trapped inside Carboniferous amber, arguing that they preserve a sample of the ancient atmosphere. While this technique is controversial and subject to potential contamination over millions of years, some analyzers have reported very high oxygen levels in these bubbles. The fossil record itself provides overwhelming indirect evidence. The gigantism in arthropods is a powerful biomechanical argument. The physics of diffusion through tracheal tubes imposes strict size limits, and the existence of animals like Meganeura and Arthropleura is simply impossible under modern oxygen levels. Their very existence is a fossilized testament to a different atmosphere. Furthermore, the global abundance of charcoal fusane in Carboniferous rocks is a clear indicator of frequent, intense wildfires which could only occur in a high oxygen environment. Finally, the existence of the coal seams themselves is the ultimate evidence. The sheer volume of coal dating from this period is staggering. It represents a quantified mass of carbon that was removed from the atmosphere and buried, using known stoichiometric ratios from the photosynthesis reaction. CO plus HO gives CHO plus O. Scientists can calculate how much oxygen would have been released for every ton of carbon buried. The math is unequivocal. The burial of the Carboniferous coal required the concomitant release of enough oxygen to push atmospheric levels to 30% or higher. These independent lines of evidence, geochemical, paleontological, and geological lodge converge on the same conclusion. They paint a consistent and coherent picture of a world with a dense, oxygen-rich atmosphere. It is a conclusion not based on a single fossil or a single rock, but on a preponderance of evidence from across the globe, all telling the same incredible story of a planet that temporarily breathed a different kind of air. We live in an age now defined by human influence on the planet, the Anthropocene. Our actions, particularly the burning of fossil fuels, the deforestation of land, and the alteration of the nitrogen cycle, are changing the Earth's atmosphere and climate at a pace that is unprecedented in the geological record. The story of the Carboniferous offers a profound, if complex, mirror to our own time. It is not a direct parallel, but a deep time lesson in the power of life to alter the planet and the unpredictable consequences that follow. The most striking parallel is the carbon cycle. The Carboniferous was defined by the massive drawdown of CO from the atmosphere through biological activity and geological burial. Our era is defined by the massive release of that same carbon back into the atmosphere through the combustion of coal, oil, and gas. We are, in effect, running the Carboniferous carbon cycle in reverse at a terrifyingly accelerated rate. Over millions of years, plants buried carbon to create our coal. In just over 2 centuries, we are digging it up and burning it, returning it to the air as CO. The result is the opposite atmospheric shift. Instead of a rise in oxygen, we are causing a rapid rise in carbon dioxide and a corresponding decline in oxygen, though the drop in O is minuscule relative to its vast reservoir and not a current concern. We are creating a super greenhouse world instead of a super oxygenated one. The consequences: global warming, ocean acidification, climate instability are our version of the extreme planetary change that ended the Carboniferous. Another lesson is the power of evolutionary innovation to disrupt global systems. The evolution of lignin by plants and the subsequent lag in its decomposition by microbes was an evolutionary accident that changed the world. Today, human technology is the evolutionary innovation that is disrupting Earth's systems. Our ability to harness fossil energy is our lignin, and the planet's natural systems are struggling to respond to the rapid change it has unleashed. The Carboniferous also teaches us about feedback loops. The high oxygen promoted wildfires, which in turn created charcoal that was even more resistant to decay, further promoting carbon burial and oxygen production. It was a reinforcing feedback loop that maintained the high oxygen state for millions of years. Today, we are triggering our own reinforcing feedback loops. Melting Arctic permafrost releases methane, a potent greenhouse gas which causes more warming and more melting. The collapse of ice sheets reduces the planet's albedo reflectivity, causing more heat absorption and further warming. Finally, the story of the Carboniferous is a lesson in resilience and change. Life did not end when the oxygen levels crashed. It changed. New forms emerged that were better adapted to the new conditions. The world moved on. This is not a comfort. However, the transition at the end of the Permian was the most devastating extinction event in history. The planet will survive our actions. Its systems will eventually find a new equilibrium. But that new equilibrium may be one that is profoundly hostile to human civilization and the biodiversity we depend on. The Carboniferous shows us that planets can exist in very different stable states. We are currently forcing the Earth out of the stable Holocene state that allowed agriculture and complex societies to flourish. We cannot know the exact characteristics of the new state we are creating, but the deep time record suggests it will be drastically different. The story of 35% oxygen is a testament to the power of life to remake a world. It is now a cautionary tale, reminding us that we have taken on that same power, and with it, a profound responsibility for the future of the only biosphere we know.